All right, welcome back, Math 213 students. Today we're going to be covering the section 7.4, the singular value decomposition. Now, if you're confused looking for the chapter 6 videos, you didn't miss them. We did, in fact, jump from chapter 5 all the way to section 7.4. This is also going to be the only section we cover in chapter 7, and in fact, the last section that we'll be covering in this class. So we do have 2 days of class time scheduled to talk about this. I haven't decided if I'm going to break the video up into 2 pieces. It's currently 11:09 p.m. And so I may get tired and decide I just want to do one half tonight and then do another half some other time. On the other hand, I may get a second wind. Sometimes when I start doing linear algebra, I get really excited, and it's hard to put it down and go to bed. The minutes just tick by, and you're having the time of your life. So we'll see if that happens tonight. I may decide to do it all in one shot. I'm especially jazzed today to be talking about the singular value decomposition. So it's not an exaggeration for me to say that this is, if not the most important, it's definitely one of the most important. It's definitely one of the most important pieces of mathematics that we teach in the undergraduate curriculum. It is a super powerful technique that is used literally in like 100 different fields in all different STEM fields and econ and different things like that. So when you see it for the first time, though, it is mighty mysterious. It's not clear why you'd ever want to do this. And so I'll start off by giving you just sort of a brief example of when you might want to do this, and then we'll get into the nuts and bolts of it. All right, so this little cutie here is named Dottie. Now, Dottie is my youngest daughter, though this picture here is pretty old. She's actually turning 6 on Monday. So I know her and a lot of her friends will be tuning in that day watching some of these videos. Just want to give her a quick shout out, wish her happy birthday. So Dottie is short for Dorothy, and my grandmother's name was Dorothy. So a lot of people, including my wife, assume that Dottie was named after my grandmother. But what a lot of people don't realize is that Dottie is also a perfectly acceptable shortening for dot product. And so the cool thing about naming a kid Dottie is that when they get older, when they sort of enter that business world or that academic world or just a more professional setting, you've really given them options for how they want to be known and sort of the identity they want to create for themselves. So keep an eye out for Dottie. She'll be doing great things in the future here. All right, so we have our picture of Dottie here, and we can think of this picture as being made up out of a bunch of pixels. Okay, some of them are lighter, some of them are darker, but together they make up the image that we see right here. Now we can also think of each of these pixels as being represented by a single number, where the number sort of determines how light or how dark that pixel should be. So we have all our pixels arranged in a rectangle. We can think of each of these pixels as being represented by a single number. So what we really have here is we have a rectangular array of numbers. Now, typically we call a rectangular array of numbers a matrix. And that's exactly what we can think of this as being just a very large matrix where each value in the matrix represents a single pixel in this image. And in fact, this image here has 1,981 rows and 2,052 columns. So this entire image is made up out of just over 4 million different pixel values, or 4 million different numbers. And so if you wanted to store this in a computer or transmit it to a friend, you would need to transmit 4 million different values in order to capture the picture. And what we'd like to do is we'd like to compress this image, or in other words, find a way to represent it using fewer values while still retaining the important overall information from the image. So you might remember from last class, we talked about the spectral decomposition. So in that case, if you started off with a square symmetric matrix, what you could do is you could break it up into these simple pieces. Each of these is an n by n matrix with rank 1. And so it gives you a way to sort of take a potentially complicated matrix and break it up into a bunch of simpler pieces. Now, this spectral decomposition only works for square symmetric matrices. If you look at the image we have right here, first of all, it's not square. It's a rectangular array. And second of all, it certainly doesn't look like it's going to be a symmetric matrix. So we can't apply the spectral decomposition here. What we can do is we can do something kind of similar called the singular value decomposition. Okay? And what the singular value decomposition does is it allows you to take a matrix and break it up into a bunch of simple pieces involving what are called singular values instead of eigenvalues and left and right singular vectors. Okay? Now, this looks like a very similar thing to the spectral decomposition, but this singular value decomposition can be used on any matrix. It doesn't have to be square, it doesn't have to be symmetric, okay? And so what you can do with this is suppose you have an image like this picture we have right here. Now what you might find is that some of these singular values are much larger than others. So for example, the first singular value might be like 100. So you might have like 100 U1 V1 transpose. Maybe the next one is like 99 U2 V2 transpose. Maybe the next one is like 98 U3 V3 transpose. And then maybe the next one is like 0.01 U4 V4 transpose. And maybe there's another small one like this. Okay. Now, what does this tell us? Well, we're able to basically take our complicated image matrix and break it up into a bunch of simpler pieces. But not all of these simple pieces sort of contribute the same amount to the original matrix. For example, because the singular values here are 100, 99, and 98, each of them contributes a considerable amount to the image. On the other hand, these singular values are all less than 1, so these pieces here, these simple pieces, don't really contribute much to the overall matrix. But somehow keeping track of the values that sort of come from here sort of is not super efficient. So what we can do is we can basically throw out these pieces because they're not really contributing much to the overall matrix. And instead of keeping all of the information that we originally had, we throw out these pieces and we really just keep track of these pieces here. Okay? Now, because the singular values attached to these pieces are much larger than the pieces we threw away, somehow you would expect that the image that you get by just keeping track of these three pieces here should be a decent representation of the image that you started out with. Okay, so this is what's called obtaining a lower rank representation of the image matrix, and we can do exactly that right here. So for example, if I only take that first piece, right, that if I only hang on to this first piece here, I get what's called a rank 1 approximation. And that's what I can draw the rank 1 approximation here. It doesn't look like anything recognizable. Okay. On the other hand, if I hang on to the first 3 terms, all of a sudden you can start to see some sort of faint images that some image that sort of looks, maybe it doesn't look like a baby. I don't know. Maybe I'm being generous here. Okay. If we keep the first 10 terms, okay, now all of a sudden you can make out the fact that it's a baby, but it's still pretty blurry. So as we start to add more terms, now this is a rank 20 approximation. This is a rank 30 approximation. 40, now we're at 50. This is 60. By the time we get up to 70 and then 80, really the images are almost indistinguishable. Okay, and for the image on the left, you have to sort of record 4 million values. For the image on the right, you only have to really keep track of 300,000 values or 322,000 values. Okay, and so it turns out you get a 13-to-1 compression of the image just by taking a lower rank representation of this image. And in fact, if you take these two images and you sort of subtract them from each other, you get a completely black square. Okay, so going back to these two images, you really can't sort of pick out the difference between these two images. They're pretty identical here. So that's one application of the singular value decomposition. Now, if you're not interested in image compression, you can imagine taking a big matrix of stock price data and somehow wanting to break it up into sort of simple components which tell you something about sort of different market trends or different factors that are affecting the market. Or you can imagine applying the same thing to data that you get from some healthcare study, or all sorts of applications. There's really no shortage to sort of the ways that you can use this technique to sort of break apart complicated looking data and sort of study it from sort of simple perspective. All right, so let's look at the nuts and bolts of it here. Let A be an m by n matrix. So the first thing I want to point out here is that we are not making any assumptions about the matrix A. It might be symmetric, it might not be symmetric. It might be square, it might not be square. It really could be any matrix that you write down, okay? So the first thing to observe is that the matrix A transpose times A will be symmetric, okay? Now this might be kind of surprising to you because, again, the matrix A could be anything. It doesn't even have to be square. But when we take A transpose times A, we will always get a square matrix, and that square matrix will always be symmetric. So this might be kind of surprising, and so it might be a good idea to see if we can understand why. Well, the first thing we should do is we should remind ourselves what it means to be symmetric. You are a symmetric matrix if, when I take the transpose, you get back the original thing, okay? So if we want to test why the matrix A transpose A is symmetric, let's take the transpose of it and see what we get. So I can bring the transpose in, but remember I have to swap the order. So this becomes A transpose times A transpose transpose. But of course, A transpose transpose is just equal to A again. So we took the matrix A transpose A, we took its transpose, and we just got the original thing back. Therefore, it has to be a symmetric matrix. Now, this is, again, this should be emphasized that A itself doesn't have to be symmetric. It doesn't even have to be square. But A transpose A will be square and it will be symmetric. All right, so if A transpose A is symmetric, then last class in section 5.4, we learned that, remember, symmetric matrices are orthogonally diagonalizable. Therefore, since A transpose A is symmetric, it can be orthogonally diagonalized. Okay. So what we can do is we can go ahead, we can find the eigenvalues of A transpose A, lambda 1, lambda 2, all the way up to lambda n. And what we're going to assume from now on is that whenever we write down eigenvalues, we're going to write them down in decreasing order. So in other words, lambda 1 is the biggest, lambda 2 is the next biggest, and so on, all the way up to lambda n, which is going to be the smallest of them. Okay. Now remember, these are the eigenvalues of A transpose A. They're not the eigenvalues of the original matrix A. Okay. Then we can go ahead and we can find the eigenvectors, v1 through vn, and we can assume that they're orthonormal. All right. Meaning that they're orthogonal to each other and each of them is a unit vector. Now you might be wondering, why are we allowed to assume that our eigenvectors are orthonormal? Well, remember, if your matrix is symmetric, like A transpose A is, then you can always pick orthonormal eigenvectors. So the next thing to observe is that if you take one of these orthonormal eigenvectors, say vi, and you multiply by the matrix A, then the length of the resulting vector squared is equal to lambda I. And that lambda I has to be greater than or equal to 0. So there's kind of a few facts here. The first is that the length of AVI squared is equal to this eigenvalue here. And the second fact is that lambda I has to be greater than or equal to 0. So let's see if we can convince ourselves why this has to be true. Well, first of all, what we can do is we know that if we're going to compute the length of AVI squared, this number here has to be non-negative, right? It's the square of a non-negative number, so it has to be non-negative itself. Okay, so in other words, we know this is greater than or equal to 0. But let's write down what this part is actually equal to. Well, remember, the length of a vector squared is just that vector dot itself. Okay. Now, remember, when we're doing a dot product, we can always rewrite this as matrix multiplication if we take the first piece and take the transpose. So this is equal to AVI transpose times AVI, where now this product here is matrix multiplication. It's not the dot product any longer. And so if we want to bring that transpose in there, it's going to be VI transpose times A transpose times A VI. And if we look at this here, A transpose times A, that's this matrix here, the one that we realized was symmetric. Okay. Now remember, these V vectors are the eigenvectors of A transpose A. So when we look right here, we see A transpose A times VI. That's just going to be equal to, since VI is an eigenvector of A transpose A, that's just going to be this thing here is going to be the same thing as VI transpose times lambda I VI. And if I pull that lambda I out, we get VI transpose times VI. But again, what we can do is we can take this matrix multiplication and we can convert it back into a dot product. So this gives us lambda I VI dot VI, and VI dot VI is just the same thing as the length of VI squared. Okay. Now remember, we were assuming that they were orthonormal. Okay. We were assuming that these VI vectors were orthonormal. So that means each of them is unit length. So that means that VI, the norm of VI squared is actually just equal to 1. So this here is just equal to lambda I. All right. So in other words, we've shown that the length of AVI squared is just equal to lambda I. And because this is some number squared, it has to be greater than or equal to 0. Okay. And that's precisely what we've written down right here. All right, so let's step back for just a second here and see what we've proved. Remember, what we've done is we've started off with the matrix A. It doesn't have to be square. It doesn't have to be symmetric. But when we compute A transpose A, this matrix is square and it is symmetric. So what we've done is we found the eigenvalues of this matrix. Then we found orthonormal eigenvectors for this matrix. And what we've done in this little proof here is we've shown that the eigenvalues for this matrix A transpose A have to be non-negative, okay? They can't ever be negative numbers. Now, for an arbitrary matrix, arbitrary square matrix, it is quite possible that you're going to get negative eigenvalues. We've seen examples of where that happens. But what we've proven here is that if the matrix is of the form A transpose A, then the eigenvalues all have to be non-negative, okay? So that's a special feature about matrices that look like this, okay? So since these eigenvalues are all non-negative, what we can do is we can take the square root of this, right? And we can take the square root of this, okay? And we're going to give those values you get by taking the square root of these things. We're going to give those values a special name. We're going to call them singular values. So the values sigma, which equal the length of AVI, or in other words, square root of lambda I, these are called the singular values of the matrix A. Okay, so you need to be careful. Remember, lambda was an eigenvalue of A transpose A. So we think of lambda as sort of belonging to the matrix A transpose A. It's an eigenvalue of A transpose A. But sigma, we think of that as sort of belonging to the matrix A. That's a singular value of the matrix A. But in order to compute it, you have to compute the eigenvalues of A transpose A. Okay? So you might be wondering, what do those singular values really tell us? Well, because the ith singular value is equal to AVI, or the length of AVI, really what these singular values are telling you is it's sort of describing how much the matrix A stretches the vector VI. Okay? So the more that the matrix A stretches the vector VI, the larger the singular value is going to be. All right, so let's see an example. Let's find the singular values of this matrix here. Now, remember, the singular values are just equal to the square roots of eigenvalues, okay? But not eigenvalues of the original matrix. We want lambda to be an eigenvalue of the matrix A transpose A, Okay, so even though we're looking for the singular values of the matrix A, we really need to compute the matrix A transpose A in order to find the eigenvalues. Okay, so let's go ahead and let's compute A transpose A. A transpose times A. 1, 1, 0. 1, 0, 1. 1, 1, 0. This is for you, Whitney. 1, 0, 1. Okay. Reading out the numbers as I write down the matrix. Special request there. So we get a 2 here. We get a 1 there and a 1 there. We get a 1 there, a 1 there, and a 0 there. 1 there, 0, and 1. Okay. Now, a few things you should observe. Remember, we said that when you ever do A transpose A, you should get a symmetric matrix. We did indeed get a symmetric matrix here, so that's good. And that's, I guess, a good observation to make. Now what we want to do is we want to find the eigenvalues of this. So we take the determinant of A transpose A minus lambda I. This will be 2 minus lambda 1, 1, 1, 1 minus lambda 0, 1, 0, and 1 minus lambda. Now, there's a bunch of ways we could do this. I'm just going to do cofactor expansion. I'll do cofactor expansion, say, along the, say, this third column here. Okay, so we're going to get 1 times the determinant of, excuse me, 1, 1 minus lambda, 1, 0. So that was in a plus spot, and then this is also in a plus spot, so we get plus 1 minus lambda times the determinant of 2 minus lambda, 1, 1, 1 minus lambda. And so this determinant here is 1 times 0 minus 1 minus lambda times 1. So this is going to be minus 1 minus lambda there. And then this determinant here is going to be 2 minus lambda times 1 minus lambda minus 1 times 1. Okay, so we have minus 1 minus lambda plus 1 minus lambda. And inside these parentheses, we're going to get lambda squared minus 3 lambda plus 1 plus 2 minus 1 is plus 1, I believe. Okay. Now we already have this factor here we can pull out, so let's pull it out. So this gives us 1 minus lambda times minus 1 plus, so we get that. Then the 1 and the minus 1 will cancel, and we can pull out a lambda. So this is lambda, 1 minus lambda, and we're left with lambda minus 3. Okay, so therefore our eigenvalues are, we've factored our characteristic polynomial. Now remember, from now on, we're going to list our eigenvalues in descending order. Okay, so lambda 1 is going to be the biggest one, that's 3. Lambda 2 is going to be the next biggest one, that's going to be 1. And lambda 3 is going to be the smallest, and that's 0. Okay, so you might be thinking, hey, we found our eigenvalues, we're done. But we're not, because remember, we weren't asked to find the eigenvalues of A transpose A. We were asked to find the singular values of the matrix here. So our singular values are the square roots of these eigenvalues we just found. Okay, so sigma 1 is rad 3. Sigma 2 is rad 1, which is just equal to 1. And sigma 3 is rad 0, which is just equal to 0. Okay, So these are the singular values that we just found, okay? Now again, just like I pointed out that whenever when we computed A transpose A, we were supposed to get a symmetric matrix. That was one indication that we did things right. Another indication is when we go ahead and find the eigenvalues, again, we shouldn't get any negative numbers. So in this case, we're in good shape. We found all non-negative eigenvalues, which is what we would expect to find in this situation. All right, so let's see a theorem here. The setup for this theorem is going to be similar to the setup that we've already been talking about. So we've got a matrix A. We're computing the product A transpose times A. V1 through Vn are going to be an orthonormal basis of eigenvectors for the matrix A transpose A. And the corresponding eigenvalues will be lambda 1, lambda 2, all the way up to lambda n. Okay? Now, suppose that the matrix A has R non-zero singular values, okay? So in other words, the first R singular values of the matrix A are going to be positive, and then after that, the remaining singular values are all equal to 0, okay? So maybe, for example, this is like rad 5, maybe this one is rad 3, maybe we go down to 1, and then after the rth one in the list, every other singular value is equal to 0. Okay, well, if that's the case, then if we take the first R eigenvectors here, so we're not going to take all of the eigenvectors, we're only going to take the first R, where R is the number of non-zero singular values. So if we take the first R eigenvectors and we multiply each of them by the matrix A, this is going to give us a set of vectors that is an orthogonal basis for the column space of A, and the rank of the matrix A is equal to R. Okay? So the important part of this theorem, I'll try, this is kind of a big theorem and it's kind of a little, there's a lot to kind of piece through here. Really, the important takeaway from this theorem is that if you have a matrix A, and if you compute the singular values of that matrix and you find out that R of them are non-zero, then the rank of the matrix A is just equal to R, okay? Or in other words, the rank of a matrix is just equal to the number of non-zero singular values that it has, okay? Now, the other part of this theorem is that the matrix, or that the vectors A times V1 up to A times VR, that this gives an orthogonal basis for the column space. That's important, but it's not going to be all that important for what we're going to do, okay? So really the takeaway from this theorem is that the rank of a matrix is equal to the number of non-zero singular vectors. Now, I'm going to prove this theorem, and you don't need to memorize this proof or anything like that, but this proof is the best proof in the course, okay? The reason this proof is the best proof in the course is because it basically touches on almost every single thing we've done in the class, okay? So if you can go through this proof with us, and if you can follow basically every step that we're doing, then it's a good indication that you kind of understand what's going on in the class, okay? And so as you're preparing for a final exam or something, it's not a bad idea to go through this proof, and if it'll kind of, if there's parts you don't understand, that'll be a good way to know sort of where you might want to focus some of your studies, okay? So we're going to focus on this part here. We're going to show that A times V1 up to A times VR is an orthogonal basis for the column space. So we want to show that it's a basis first, okay? So the first thing we're going to do is we're going to show that, well, what does a basis have to satisfy? It has to span and it has to be linearly independent. So we're going to show, first of all, that these vectors, that the span of these vectors, so the span of AV1 all the way up to AVR, we're going to try and show that the span of these vectors is equal to the column space of A. Okay? Well, if a vector y lives inside the column space of A, then one of the facts we saw earlier, not earlier today, but early in the course, is that if y lives inside the column space, that means that there is a vector x, so that when you multiply A times x, it gives you the vector y, okay? And this is for some vector x in Rn. Okay? All right. So we're going to start off with a vector y that lives inside the column space. What we want to do is we want to show that this vector y can be written as a linear combination of these vectors here. Okay? If that's the case, then it proves that these vectors here span the column space. So we pick some vector x so that a times x is equal to y, and that's possible because y lives inside the column space. Now, since the vectors v1 up to vn, remember these vectors here, they form a basis for Rn. Okay, so since x is a vector inside of Rn, and this is a basis for Rn, we can write x as a linear combination of these vectors here. Okay, now it's important to sort of know the distinction here. Okay, so let me just write this down here. Okay, so because this is a basis for Rn, because x lives inside Rn, that means x can be written as a linear combination of these vectors for some scalars c1 through cn. Okay, so notice here we're using all the vectors v1 through vn. Okay, here we're only using the vectors av1 up to avr, so we're only using the first r of them, whereas here we're sort of taking all n of these vectors over here. Okay, so well, what can we say? Well, remember, a times x is equal to y. So what we're going to do is we're going to multiply both sides of this equation by the matrix A. Okay, so we get a times x here is equal to a times c1 v1 plus all the way up to cn vn. Okay, now on the one hand, a times x, well, we said that a times x was equal to y. So over here, we get the vector y. Over here, what we can do is we can distribute the matrix A through. So this is going to give us c1 av1 plus, I'm going to write it out in a little bit more detail. So cr avr, so this is the rth one, plus cr plus 1 a vr plus 1, and then cn a vn. Okay, so I've just kind of expanded this sum out for a little bit. Okay, now remember, we have this fact that the length of the vector a v I, okay, so the length of the vector a v I is just equal to the singular value, the ith singular value. Okay, so if we go back to our assumption, remember, we're assuming that every singular value after the rth singular value, we're assuming that each of these singular values is equal to 0. Okay, so the length of this vector is just equal to, the length of this vector here is just equal to the r plus 1 singular value. But we assume that the r plus 1 singular value is equal to 0. So therefore, this vector here has to be equal to 0. And we could do the same thing with the next vector and the next vector. All the way up to this vector here, the length of the vector a times vn is just equal to the nth singular value. But again, we were assuming that that's equal to 0. And therefore, this vector here has to be equal to 0. Okay? So every vector that shows up in this line after the rth one has to be equal to 0. And so therefore, what are we left with? Oops, wrong color pen. That would be confusing. What we're left with is just c times c1 times av1 plus c2 times av2 all the way up to cr times avr. Okay? And so what we've done is we've shown that the vector y can be written as a linear combination of the vector av1, av2, all the way up to avr. Okay? In other words, you can write down the vector y using only these vectors up to the rth one. Okay? And therefore, because y can be written, anything in the column space can be written as a linear combination of these things, it shows us that the span of these vectors is equal to the entire column space. All right, so let's just write down what we've concluded. So what we've concluded is that the column space of A is equal to the span of these vectors here, AV1 up to AVR. Okay. Now, ultimately, we want to show that these vectors are a basis for the column space, so we need to show that they're linearly independent. Okay. We're going to kind of do that in a bit of a roundabout way. So notice that since, remember, we assumed that our vectors, our eigenvectors V, Vi, these were orthonormal. Okay. So in particular, these eigenvectors here are orthogonal to each other. Okay, so what we can do is if I take the vector AVI and I take the dot product with the vector AVJ, well, again, I'm going to write my dot product as a matrix product by taking the transpose of the first part. Okay, and then I can bring this transpose in by swapping the order. So this becomes VI transpose times A transpose times A times VJ. Okay. Now remember, VJ is an eigenvector for the matrix A transpose A. Okay. So since VJ is an eigenvector for A transpose A, this matrix product here is just equal to VI transpose. So this is just equal to lambda J times Vj. Okay. And what I can do is I can pull the lambda J out front, and I'm left with Vi transpose times Vj. And again, we can turn this into matrix multiplication if we get rid of that transpose. Or sorry, we can turn it into dot product if we get rid of the transpose. And we end up with this. Okay. But remember, Vi dot Vj is equal to 0 because the eigenvectors were orthogonal to each other. So this gives us lambda j times 0, which is just equal to 0. So what we've done is we've shown that the dot product of AVI dot AVJ is equal to 0, and therefore the vectors AVI and AVJ are orthogonal. Okay. Now, this isn't quite enough. Okay, so remember, we want to prove that these vectors are linearly independent. Now, proving that they're orthogonal to each other is not quite enough to show that they're linearly independent, because it's possible that one of these vectors might be 0, or at least some of them might be 0. However, remember that the length of AV1 is equal to sigma 1. The length of the vector AV2 is equal to sigma 2. And all the way down the list, the length of AVR is equal to sigma r. Okay. So the length of each of these vectors is just equal to the corresponding singular value. And remember, we were assuming that the first r singular values were all non-zero. Okay. So in other words, since each of these, the length of each of these vectors is equal to a singular value, and since sigma 1 is greater than or equal to sigma 2, which is greater than or equal to all the way up to sigma r, and all of these are greater than 0, this implies that AV1 all the way up to AVR are all non-zero vectors. Okay, hence the set AV1 up to AVR is an orthogonal set of non-zero vectors and is linearly independent. Okay. So what we've shown is we've shown that these vectors here span the column space. We've shown that these vectors here are all orthogonal to each other. And we've shown that these vectors are also linearly independent. Okay? And so therefore, since they span and are linearly independent, it tells us that they are a basis. So in other words, these vectors give us an orthogonal basis for the column space of A. Okay? And that was what that part of the theorem was telling us. Okay? Now the second part of the theorem was concluding what the rank of the matrix is. But remember, the rank of a matrix is just equal to the dimension of the column space of the matrix. Okay? And remember, the dimension of the column space is just equal to the number of vectors you have in a basis for the column space. So since we proved that this is a basis for the column space, and since there's r vectors in there, our rank has to be equal to r. All right, so that was quite a hefty theorem to prove, okay? But I like this proof because it really contains so much stuff from the class. We talked about the column space. We talked about orthogonality. We talked about eigenvalues. We talked about linear independence. We showed that something spanned. We talked about the rank. Really, like, if you can understand all the steps of this theorem, you know, it means that you're in pretty good shape, you know, as far as your understanding of a lot of the content in the course goes. So again, we won't ask you to reproduce this on a final or anything, but it's a good metric on how well you understand things. All right, so what is a singular value decomposition? Well, a singular value decomposition, you can kind of think of it as being like an analog of diagonalizing a matrix. Okay, so remember when we were diagonalizing matrices before, maybe we had something like this. Okay, we would look for our P matrix and our D matrix, and we would always want our D matrix to be a diagonal matrix, a square diagonal matrix, okay? And it would always be the same shape as the same size as the matrix A, okay? Now, we're going to basically be doing the same thing, okay? Except the problem is that we're not only restricting ourselves to square matrices. We're thinking about any matrix possible, right? So it could be square, it could be not square, it could be whatever shape or size. Now, if our matrix A is not square, what that means is it means the matrix that goes in the middle here won't be able to be square either, okay? It'll have to be the same shape as the matrix A. So if our matrix A is not square, then the matrix that goes in the middle will not be square either, okay? So we really can't just sort of think about diagonal matrices. We sort of have to generalize our viewpoint a little bit. And so instead of just thinking about diagonal matrices, we're going to think about these sort of, I don't know, they don't really have a name, but they're kind of like fake diagonal matrices. And what do I mean by that? Well, essentially they look like this, okay? In the top left corner, you've got an honest to goodness diagonal matrix. And then what you do is you fill up the rest of the matrix to the desired size with zeros everywhere else. So expand it out a little bit. What does this look like? Well, in the top left corner, we've got an honest to goodness diagonal matrix. And then if we want to make our matrix a certain size, all we do is we fill up the rest of it with zeros everywhere else, okay? And so if we fill it up and make it a not square matrix, then it won't be an honest diagonal matrix, but it'll still sort of have this diagonal piece in the top left, okay? Now, another thing to point out, well, and so we're going to call this matrix sigma. We're not going to call it D because it's not honestly a diagonal matrix, but we'll call it sigma for the rest of the section, okay? Now, the thing to remember is when we were diagonalizing the matrix A, the values that we put along the diagonal were the eigenvalues of A. We're going to do something similar, but remember, because now our matrix A doesn't have to be square, it might not have eigenvalues. What we do instead is we put the singular values of the matrix A along the diagonal here, okay? So it's it's similar to sort of the diagonal matrix we found before, but A, it doesn't have to be a square matrix, and B, it doesn't have the eigenvalues along the diagonal, it has the singular values instead. Okay, but this matrix sigma here, this is going to fill the role of our diagonal matrix when we do the singular value decomposition. All right, so let's see what the big theorem says. So let A be an m by n matrix with rank R. Okay, so remember what the rank, if the rank is R, that really tells us that the first R singular values are all positive, and then all of the singular values after that point are equal to 0. Okay, so if you have an m by n matrix with rank R, then what you can do is you can split it up like this. A is equal to U sigma times V transpose, where sigma is one of these diagonal matrices. I'm going to put it in quotes because it's not really a diagonal matrix. It's actually not even square. But it's one of these kind of fake diagonal matrices. It's the same size as the matrix A, and it has singular values on the diagonal. Okay, so that's where the matrix sigma comes from. It's a matrix that's the same size as A. You put the singular values along the diagonal, and then you fill up the rest of it with 0. Okay. The matrix U is going to be an m by m orthogonal matrix. The matrix V is going to be an n by n orthogonal matrix. And when you multiply them all together like this, you should get the matrix A back. Okay, so I haven't said yet where you how you find the matrix U or how you find the matrix V, but whenever you take a matrix A and you split it up in this way, we would call it a singular value decomposition of the matrix A. The columns of the matrix U are called the left singular vectors of the matrix, whereas the columns of V are called the right singular vectors. So the columns of U go on the left, the columns of V, so the columns of U go on the left, that's why they're called left singular vectors. The columns of V go on the right, that's why they're called right singular vectors. All right, so you may be thinking back to your diagonalization days where you would say take a matrix A, and suppose you're doing orthogonal diagonalization, you would write it down as PDP transpose. Now, obviously this looks quite similar to this, right? You're breaking it up into the product of three matrices. One of them sort of looks diagonal, and then you're taking the transpose of the third one. So there's kind of some similarities to the pattern in which we've broken up these matrices. Now you might wonder, well, how come in diagonalization or orthogonal diagonalization, how come I'm able to use the same matrix on the left and the right? Okay, and ultimately one way to think of it is if you're taking a matrix A that's square, if you think of just how the sizes of these matrices work out, you're sort of you can do that because sort of the sizes of the matrices work out in some nice way. Okay, whereas over here, if your matrix is not square, you have to have an m by m piece here and an n by n piece here. Otherwise, you can't sort of piece these orthogonal matrices together in this way. So just the very fact that our matrices aren't square sort of forces us to have different matrices here on the left and on the right. Okay, and that's sort of one reason why we can't just sort of hope to find something that looks like this. So sort of geometrically, what is a singular value decomposition doing? Well, remember, we can kind of think of a matrix as taking sort of vectors and transforming them. So suppose we have sort of our vectors, and our matrix A sort of takes these vectors and sort of skews them and stretches them in this way. Well, instead of sort of doing this transformation all at once, we can think of this transformation as sort of being broken up into three pieces. The first piece is that we're going to take our vectors and we're just going to rotate them in the plane. So it looks like we've sort of rotated them by like, 45 degrees or something like that. Now, a rigid sort of rotation like this, you can think of that as sort of being an orthogonal matrix. So we can sort of we realize this transformation by multiplication by an orthogonal matrix. Now what happens is once we have our vectors sort of rotated, what we can do is if we multiply by one of these sort of fake diagonal matrices, what this does is it's going to stretch our vectors in the principal directions. So it's going to stretch it sort of in the horizontal direction, and it's going to stretch it in the vertical direction. But it's a very sort of straightforward way of transforming it. It sort of just stretches it in the vertical and stretches it in the horizontal. Okay. Now, once we've done that, we can then sort of take this picture and we can rotate this picture to get the final thing. And again, this rotation that we get here is obtained by multiplying by some orthogonal matrix, okay? So we can either think of doing our transformation all at once, okay? Or we can think of breaking it up into this product of these three transformations, which would be just, so we take our vector x, we would rotate it by v transpose first, then we'd rotate it, or then we'd multiply it by sigma, and then we'd rotate it again by u, okay? And the claim is that's the same thing as just doing a to the vector x in one step, okay? So that's kind of the picture of what's going on. It definitely takes some thought to kind of wrap your head around what's going on, but this is sort of the underlying picture to keep in mind if you'd like. All right, so at this point, you're all dying to know, how do I compute a singular value decomposition? I've told you how to find the sigma part, but let's figure out how to find the rest of the components of a singular value decomposition. So let's compute, so here's sort of the step-by-step way to compute the singular value decomposition of a matrix A, which is, we want to split it up into U times sigma times V transpose. So the first step is we're going to compute the matrix A transpose A. We're going to find its eigenvalues, and then we're going to find an orthonormal basis of eigenvectors for the matrix A transpose A. Now, once we've found the eigenvalues and these eigenvectors, we're actually, a lot of the way done. So if we know what these eigenvalues are, we can compute the singular values. And once we know what the singular values are, we can build the matrix sigma. So sigma is just the m by m matrix. And again, it's one of these fake diagonal matrices, where the entries along the diagonal are just the singular values listed in decreasing order, okay? Now remember, sigma is going to be the same shape as the original matrix M. So we've gotten our sigma, that tells us how to make our sigma matrix. The way that we find our V matrix is we just take these orthonormal eigenvectors that we found and we plug them in as the columns of the matrix V, okay? So these eigenvectors, these VI, they become the columns of V, which, again, remember, V transpose is what shows up in the formula. So these little V vectors, they become the columns of V or the rows of V transpose. So you just have to kind of keep in mind that these vectors become the columns of V, but when you actually plug them into the formula, because you're taking the transpose, they'll end up becoming rows, okay? So that tells us how to find our sigma matrix and our V matrix. How do we find our U matrix? That's the big question of the day. Well, we have a formula for computing the columns of U, and it turns out that the first R columns of the matrix U can be computed by just taking A times VI, we've already figured out what the VI are, and then dividing by sigma I, okay? Now that's going to sort of allow you to find the first R columns of the matrix U. Now the problem is in some situations that won't be enough. So for example, maybe our original matrix A is like a 3 by 2 matrix. Well, in that case, V is going to be 3 by 3. So we're going to have 3 eigenvectors for the columns of V. Nope, that's a lie. That is a blatant lie. Okay, sorry, we're going to have 2 eigenvectors for the columns of V. And so we can take these 2 vectors and we can plug them into this formula here, and it's going to give us 2 columns for the matrix U. But the problem is the matrix U is a 3 by 3 matrix. So in this case, we would need to find one more column for the matrix U. So what we have to do then is, in this situation, we would have to expand, we'd have to take the U vectors we already have, and then we'd have to find extra vectors that are orthonormal or that are orthogonal to these U vectors, okay? So in other words, we'd have to take the vectors we already get. We'd have to take the vectors we get from using this formula, and then we'd have to find extra vectors that are orthogonal to these vectors, okay? And once we find enough orthogonal vectors, we would normalize them until we get an orthonormal basis here. Okay? And then once we have these vectors, they become the columns of the matrix U. All right, so this seems like a good place to pause. We've done a lot today. We've been introduced to a lot of the leading characters in the singular value decomposition. We've also gone through the steps to compute it. The only thing we have left to do is actually sit down and compute one. Now, as you can imagine, there are quite a few steps involved in this, and so it ends up being a bit of a time-consuming process, but they're all steps that we've seen before, so as long as you keep your cool, keep your wits about you, and remember sort of which steps to do in what order, you'll find it to be a pretty enjoyable and pretty relaxing experience. So we'll come back with some examples next class. So until then, we'll sign off and be back with a thrilling conclusion next day. Stay healthy. Remember to like and subscribe, and do something nice for your mothers.